Welcome to this explainer. Today, we're diving straight into one of the most fascinating cosmic mysteries out there, hot Jupiters. These are quite literally the darkest known objects in the universe. So if you've ever found yourself wondering what's actually hiding out there in the absolute pitch-black corners of space, well, you are in exactly the right place. Let's just jump right in.
Okay, look at this number right here, 99.9%. We're talking about a distant exoplanet named TRES 2b, and this number, it represents the astonishing amount of visible light that this planet simply absorbs. To really put that into perspective for a second, think about coal, which is, one of the darkest substances we have here on Earth. Coal absorbs about 95% of the visible light that hits it, but TRES 2b, it absorbs 99.9%. It is a completely light-thirsty world, blacker than coal, absorbing almost every single photon that heads its way.
But right off the bat, this raises a really, truly fascinating question. How do astronomers actually go about finding a pitch-black planet in the pitch-black void of space? It's kind of like a giant cosmic detective mystery. I mean, we are looking for something that is practically invisible, drifting hundreds of light years away from our own solar system. How do you track down an object that seemingly swallows the exact thing we use to look for it, light?
That brings us to Section 1, the suspects. Meet the shadow worlds.
The sheer scale of the extremes we're dealing with here is staggering. Let's look at our three primary suspects. First up, we've got TRES 2b, located 750 light-years away from us, soaking up that mind-bending 99.9% of light. Then there's WASP 12b, a staggering 1,400 light-years away, and that one absorbs at least 94% of visible light. And finally, WASP 104b, sitting 466 light-years away over in the constellation Leo, absorbing somewhere between 97 and 99% of the light that hits it. Now, detecting anything at 1,400 light-years is incredibly hard, but detecting a void, that is an absolute masterclass in astrophysics. These distances are immense, but their unparalleled ability to just gobble up starlight is the thread that connects them all.
And when researchers using the Hubble Space Telescope actually analyzed WASP 12b, they really didn't hold back. They literally described it as black as fresh asphalt. We're not talking about a dark gray planet here or some dimly lit sphere. We are talking about massive gas worlds that are completely, totally devoid of reflectivity. They are absolute voids in the sky.
Moving on to Section 2, the anatomy of a shadow, why so dark?
Well, it really all starts with the nature of a hot Jupiter. These are gas giant planets, much like our own Jupiter, but with one massive, game-changing difference: their orbits. Take WASP 104b, for instance. It sits just 4.3 million kilometers from its star. Because it's tucked in so incredibly tight, it completes a blazing fast orbit in just 1.75 days. Think about that. Its entire year is less than 2 Earth days. And as you'll see in a second, this extreme proximity is absolutely crucial to their darkness.
To really understand this, let's contrast them with our own familiar Jupiter. Jupiter is swathed in these bright, beautiful clouds of ammonia, and it basically acts like a giant mirror, reflecting over a third of the sunlight that reaches it. But these hot Jupiters, they're simply way too hot for any reflective clouds to survive. So instead of shiny ice or ammonia clouds, they have this incredibly thick, toxic, hazy atmosphere. It acts more like a massive sponge, just deeply absorbing the light instead of bouncing it back out into space.
And just how hot are we talking? Check out this blistering temperature for WASP 12b, 2,538 degrees Celsius. At these extreme, melting temperatures, it is physically impossible for reflective ammonia or ice clouds to even form. The molecules just cannot survive that kind of heat. So without those shiny clouds to bounce the starlight away, the light penetrates deep, deep down into the planet's atmosphere, where it just gets entirely absorbed by hydrogen and converted straight into intense heat.
All of this comes together to create the ultimate recipe for a dark planet. First off, they're tidally locked. Basically, that means one side is a permanent, scorching day, while the other side is stuck in perpetual night. Add in that total lack of reflective clouds we just talked about, and then factor in their chemical makeup. The atmospheres of these worlds are just packed with light-absorbing chemicals. We're talking vaporized atomic sodium, gaseous potassium, and gaseous titanium oxide. These elements brew up a dense, toxic haze on that permanent day side that literally just eats up the visible light.
Which takes us to Section 3, catching the invisible, the transit method.
So if they act like a sponge and eat all the light, we're back to our big detective question. How on Earth do we actually find them? Well, the brilliant workaround here is that astronomers don't actually look for the planet itself. Instead, they stare intensely at the star it orbits. When a planet transits, meaning it passes directly in front of its host star, it blocks a microscopic fraction of that starlight. This causes this tiny micro-dimming effect. Satellites, like NASA's Kepler Space Telescope, are specifically designed to monitor stars and hunt for these incredibly tiny, periodic dips in light. By measuring that specific dimming, astronomers can prove the planet is there, and they can calculate exactly how little light the planet itself is reflecting.
And I've got to say, the precision required to pull this off is just mind-blowing. Over 50 orbits, the Kepler Space Telescope detected a brightness change of just 6 parts per million for TRES 2b. Let that sink in. 6 parts per million. That is the smallest ever change in brightness detected from an exoplanet. It's kind of like staring at a sprawling, brightly illuminated metropolis from miles away and noticing a single solitary light bulb flickering out. Through that microscopic fluctuation, scientists were able to deduce that the planet was retaining almost all the light that hit it, directly proving its profound lack of reflectivity.
But wait, because here is Section 4, the twist, the glowing truth.
Just when we think we have these shadow worlds all figured out, there is a pretty massive plot twist. It turns out labeling them the darkest planets might actually be slightly misleading. Here is the glowing truth. These planets aren't pitch black at all. Because of their immense thousands of degrees thermal heat, they actually glow. Now, it's not a bright, shining light. It's a thermal glow. They emit this faint, bruise-like purple or a deep, dull red light. If you could somehow safely see them up close, researchers say they would look a lot like a burning ember in a fire pit or, the red-hot coils on an electric stove. So they don't reflect light, for sure, but they absolutely radiate their own eerie, menacing heat.
Which brings us to one final lingering mystery. Even when we factor in all those extreme chemicals, the vaporized sodium, the potassium, the titanium oxide, our absolute best models still cannot account for all of the missing light on planets like TRES 2b. The math just doesn't fully add up. Researchers actually believe there's an unidentified mystery element floating around in these atmospheres, acting as an extra, unknown light-absorbing ingredient. And this is exactly why this stuff matters. Every time we think we understand the rules of the cosmos, a shadow world comes along and rewrites them entirely. So what exactly is this missing ingredient? And honestly, what other incredible invisible wonders are just waiting out there in the dark? Thanks so much for joining me on this explainer. Keep looking up and always keep questioning what you can and cannot see.